Hello everyone, my name is Chirag Birla. I work as an electrical engineer in the power supply group at Brookhaven National Laboratory. In this video, I will present an alternate method for measuring the loop gain of a power supply. I'll be going over the theory as well as a hardware demonstration method. I love questions, so please feel free to reach out to me with any. Today, I will demonstrate an alternate method of measuring the loop gain of a power supply. To give some context regarding this measurement, I was testing a power supply which I had to characterize by performing step response, noise measurements, and the loop gain. Initially, I started by doing the loop gain measurements using the middlebrook method, and then I realized that with respect to my system, there's another way that I could use to measure the loop gain. So let's look into that. Let us compare the standard method, which is using the middlebrook criterion, with the method that I'm proposing. Just a little bit of background uh, regarding the power supply system that I was performing the loop gain measurements on. Initially, I used the Middlebrook criterion of signal injection and experienced noise issues in the low frequency range, which gave me bad readings uh, on the gain and the phase, particularly on the low frequency regime. What I mean by that is, suppose this is my frequency on x-axis, gain, phase. I had noise in the low frequency and my phase was also all over the place. So this was an issue in my case. Uh, I wanted to obtain clean readings in my field where the power supply uh, must operate reliably with high precision. We use error signals, which is basically the subtraction of the reference signal and the feedback signal in real time to gain insights about the performance of the power supply. So when I use the alternate method, which exploits the availability of the error signal to perform the loop gain measurements, the noise issue went away. So I'm going to explain how it works. On the left side, we have our standard loop gain measurement method. By breaking the loop using an injection resistor, which is used to inject the AC signal for the loop gain measurement. And from the representation of the power supply blocks here, I can obtain an expression for the loop gain, which is T of S. I'll write it here. T of S is Hs times Gc of S times Fm times Gp of S. So it is the multiplication of all these transfer function blocks. On the right side, I have my proposed method where I'm using a unity gain summing or error amplifier to subtract the reference signal from the feedback signal. Please note, I'm inverting the feedback signal, which is basically the voltage divided output, uh, and it is being inverted by this inverting amplifier here with a gain of 1. My reference signal comes in through a buffer amplifier here and this signal goes into the summing amplifier's inverting terminal. So I have two signals going to the inverting terminal of the summing amplifier, V reference and minus V feedback, and the output is minus 1 times V reference minus V feedback. So this is what I'm calling as an error signal. This error signal goes into the compensation amplifier GC of S through the PWM block here, FM, and the power stage GP of S to give me an output voltage as desired from the reference signal. So over here, I can write some equations to obtain a loop gain expression. So first of all, my V feedback is simply V out times the transfer function H of S. So that's my first equation. V feedback of S, H of S times V out. That's my first equation. My second equation uh, is now on a similar note, I reach V output when this error signal goes through all these transfer function blocks. So my error signal goes here to this transfer function block and I get an output voltage. So I can write the second equation as V error of S is, I'm sorry, V error of S times GC of S. I'm sorry, FM times GP of S is V out. That's my second equation. And now I can substitute V out from equation 2 into my equation 1 and I obtain an expression which looks like this. V feedback by V error of S is HS times GC times FM times GP, which is nothing but my loop gain expression. And of course, this is same as what I obtain using the classical method. So in the next slide, let me show you how my power supply system looks like and explain how I'll be performing the loop gain measurement using this alternate method. So this is my power supply uh, representation and the measurement setup for the loop gain measurement. Over here, I have a screenshot of the alternate method from previous slide, just as a reference. In this system, I'm regulating the output voltage on the resistive load uh, through a linear pass amplifier, which is being fed by a DC power supply. Uh, this linear pass amplifier is basically a transconductance amplifier. It has three MOSFETs in parallel, and I have an active current sense for each of the MOSFETs. Uh, since I work on high voltage and high current applications which require high precision and low noise, linear amplifier works well here at the cost of some power loss. Uh, Basically, this system is uh, is like your typical linear voltage regulator, such as LM7805, which regulates the output voltage on the load. Uh, and it is immune from any disturbances from the input side. So in my system, I sense the output voltage through a voltage divider, which is same as the HS block in my reference diagram. This voltage feedback signal goes into an inverting amplifier with a gain of 1, and I get a inverted V feedback signal, which is also what I have in my reference diagram here. I have a reference signal which comes in through a buffer into the summing amplifier's inverting node. And then the summing amplifier sums the signal from of V reference and the inverted V feedback signal to give me an error signal with a gain of unity. So in my system, these three resistors are of same value. So this makes the summing amplifier with a of gain 1. And then it goes through a compensation network into the series pass linear amplifier to regulate the output voltage. So my combination network is same as the GC block here. I don't have any PWM, so this FM blocks get eliminated. And my power stage is my series pass linear amplifier block here. I am monitoring V feedback on channel 3 and V error on channel 4 on the scope MSO56B. It also has an inbuilt arbitrary function generator, which I'll be using to provide my reference signal uh, to this voltage controller board. Another scope, uh, which is MSO 4054, I'm measuring the load voltage on channel 1, and I'm using a splitter to split my function generator so that I can also monitor the reference signal on channel 2 on this scope. I will do the loop gain measurement through a control system license that is inbuilt in the MSO 56B scope. The loop gain measurement will use channel 3, which is V feedback, as the output source, and channel 4, V error, as the input source. While the power supply is at a DC operating point, the arbitrary function generator will inject an AC signal of desired amplitude and sweep through the range of frequency to obtain the loop gain measurement of the power supply. So here's my measurement setup. Let me just walk you through. This is my DC power supply. It's a AMITech SGA 40125 model, capable of 40 volts at 125 amps. This one is connected to my series pass linear amplifier, which is a 3-stage series pass linear amplifier. It has 3 MOSFETs in parallel. The source is going to the load, which is right there, the one with the 2 fans. That's a 0.2 ohms load, 6 kilowatts max power. That's what I have available right now, so I'm using it. I'm sensing my output voltage using this voltage divider board that I made. These leads are going across the output load, and then through the divider network I have my feedback signal going into my voltage controller board. I have a function generator that's inbuilt in my scope. As you may be able to see, I have many options: square, pulse, ramp. On my scope, on channel 3, I'm measuring V error signal, which is right here. And on channel 4, I'm measuring my V feedback signal. There's another scope, which is right here. On this scope, I'm measuring the output voltage and my reference signal that's coming out of the BNC in the back of this scope. Because when I'll be doing the loop gain measurements, I will not be able to see my output voltage and the reference signal if I have them connected to this scope, which will be doing the loop gain measurements. So I just want to take a look so that everything is going as expected while the measurement is being done. Now I shall bring my power supply system to an operating point where I'll be doing the loop gain measurements. So I'll put my reference signal back to the scope on channel 2. I'll change my function generator to DC. And let me make my offset 0 to begin. And I'll turn on my power supply. So as you can see, it comes up to 8.1 volts. Uh, that's the voltage drop that I would like to maintain across my series pass stereo amplifier. So as I'll go up in current, I will adjust my voltage knob approximately to maintain a 8 volts drop across my series bus. So let's make so I'll turn this up. And as you can see, my current is increasing. So I've brought up my power supply at 12 volts, approximately 21 amps. And across my series bus, I have this multimeter connected, which is measuring 8.5 volts. So this is my operating point where I'll be doing my loop gain measurements. As you can see, I'm measuring 3, 4, 5, 6, 7. So approximately 3.75 volts across the load on channel 1. And channel 2 is my reference, which is approximately 1 volt. For my loop gain measurement, this is the menu on my scope. For input source, I'll select channel 4, which is my my V error signal, and channel 3 is my output source, which is my feedback signal, which is being measured on the voltage controller board. I have an internal oscillator. I select high impedance. Analysis method is spectrum mu. I'll select 15 points per decade. I think that's sufficient. My frequency of interest is from 20 Hertz to 20 kilohertz. I'll select a amplitude profile for my signal. So this is the amplitude profile that I've selected. The scope will use spectrum average to measure the gain, and will use the time delay between the two channels to measure the phase. So once I've pressed power preset at 1 volt reference operating point, the loop gain measurement will start. So yes, press power preset, and then I press run, stop. So as you can see, it's using spectrum view to get an idea about the gain. And on this scope, as you can see, yeah, I have my output voltage and my reference signal. So once this measurement is done, I will show you the results. Okay, so my loop gain measurement is done. As you can see, let me just make this bigger. Okay. As you can see, the gain is the green trace and the phase is the red trace. Is my phase margin is minus 128 degree at 3 kilohertz. So that's about 52. Am I right? Yeah, 52 degrees of phase margin. Let me just export this to my PC and I'll compare this to my simulation results. So this is my loop gain measurement that I've imported from the scope into my laptop. This green trace, once again, is my gain response. The red trace is my phase response. The green trace or the gain crosses 0 dB axis at 3 kilohertz with a phase of minus 128 degrees, which comes out to be 52 degrees of phase margin. If I compare this to my simulation results, this is my simulation result. It crosses 0 dB at around 3.6 kilohertz with a phase of minus 125 degrees. Which is not the same, but it's quite close, and I think it is satisfactory result in my case. If I compare other frequency points, let's say 20 hertz, where I start, I have a 40 dB gain from my simulation, which is same as from my measurement. In my measurement, the peaking occurs around 600 hertz. In my case, it occurs around 700 hertz. And if you look at the shape of the gain and the phase, they are quite similar. For my measurement and my simulation. One more thing that I wanted to show you is that I did a step response, and this is the measurement, and this is my simulation. As you can see, my output voltage step response looks quite similar for my measurement as well as my simulation. So to summarize, the alternate method of loop gain measurement works given that we have access to the V-error signal. Typically, V-error signal is not available in feedback systems. In digital feedback systems, and especially in digital controllers, which is quite widely used nowadays, we have access to V-error signal. Hence, the alternate method works there for T of S measurement. Thank you.